Boolean algebra is the branch of algebra in which the true values of variables are denoted by true or false, usually represented with 1 for true or 0 for false. Boolean algebra is also used in discrete math for computer arithmetic and logic operations. It is used in both computer science and computer engineering for development of digital electronics using logic gates, and it can be found in all modern programming languages. Let us take a look at Boolean operations, which are and, or, and not, Boolean operators, also known as logical operations. Next, we will take a look at an example for the operation not. In this example, we are using the variable p to represent this preposition. P, it is raining outside. Not P, it's not raining outside. This truth table visually displays the preposition. Notice we have included the 1 and 0 in this truth table, as it's usually what is displayed in Boolean algebra. The not operator is the same negation we saw before. Notice that not P in Boolean algebra is denoted with a bar above the letter to indicate negation. Keeping up with our theme of rain, let P be it's raining and Q be I have an umbrella. This example is demonstrating the AND logical operator to combine this preposition. If it's raining and I have an umbrella, I will go outside. Now, let us look at this truth table to see how Boolean algebra is performed using conjunction and logical operation. As you can see from the table, there is no difference from this table from the ones we saw when looking at preposition. P conjunction Q is true when both variables are true. In this example, we are demonstrating the OR logical operator as used in Boolean operations. If it's raining outside or I have an umbrella, I will go outside. Using letters to replace the statement, we can mathematically write P disjunction Q. Here again, we see the truth table is the same, where you have the truth output as long as either variable has at least one true variable. Let us look at some of the Boolean algebra rules. You may ask, why are we repeating details we have already covered elsewhere? This is because apart from using the 3 Boolean operations to work with preposition, Boolean algebra also has many important laws which it uses to reduce Boolean expression to their simplest terms. In cumulative law, the order does not matter. You can swap the object and the output will be the same for both and all operations. With the associative law, it does not matter how we group the object. The output is the same for both and all also. The distributive law is analogous to multiplying out the brackets in traditional algebra. These Boolean algebra laws we have just looked at are used in logic proofs, as we will see shortly. DeMorgan is another common Boolean algebra law. It uses a pair of rules to translate statements and to simplify Boolean expressions. Notice the DeMorgan law has these 2 rules where it allows via negation the disjunction and conjunction completely in each other's terms. As shown here in this example, P conjunction Q negated is the same as P negated conjunction Q negated. And the same for P disjunction Q is the same as P negated disjunction Q negated. Now we will go through this example interactively. Here we have a universal set, then we have members of P, and we have members of Q. P union Q gives us the members that are found both in P and Q. Therefore, this P union Q negated will be the members that were left behind, and that is 1, 3, 11, and 13. Now here we show members that are not found in P, and here we have members that are not found in Q. When we perform P negated intersection Q negated, then we are left with the results that is 1, 3, 11, and 13. Hence, P union Q enclosed in brackets negated is the same as P negated intersection Q negated. Hence, we have proved that the first DeMorgan law is true. We can also display the DeMorgan law theory using a truth table, as we can see here. Notice that the last two columns are the same, proving that P union Q negated is the same as P negated intersection Q. Applying the DeMorgan logic law, we can now prove that the logic proofs do use Boolean logic law rules. Let us go through an example. Here, we can factor out P out of both the terms. Then we apply the identity P plus 1 and get P. Then we apply the identity of P plus 1 again and we get P. This is how we do simple proofs in Boolean algebra. In summary, we saw that Boolean algebra has operations that rely on Boolean operations, logic proofs, and DeMorgan's laws to simplify the Boolean expression to their simplest form. And this is useful in computer science for making programs efficient by using less memory when the expressions are simplified to their simplest form.